Okay, so in our previous videos, we have introduced series and sequences, the difference between them, and the difference between the limit of a sequence and the limit of a series. And we have in fact introduced the nth-term test for divergence, which is a test that usually studies the limit of the sequence in order to determine if the corresponding series is divergent or not, but it tells us nothing about the convergence of the series. So, however, the nth-term test of divergence can only help us determine if a series is divergent. So in some cases, it cannot really tell us if a series is convergent or not. The test is inconclusive. So this is why there are several tests of convergence of series. And we're going to start here with the first one, which is the integral test for convergence. So if we start by considering a sequence un, which is defined by un equals to f of n, where n is a positive integer. So over here, the sequence is defined by an explicit expression, which is a function in terms of n, where f is a continuous function over one positive infinity. So it's very crucial for f to be continuous. So the integral test tells us that if the integral from 1 to positive infinity of f of x dx converges. Now, this is an improper integral. Usually, improper integrals have infinite as one or both of their bounds. Okay, and an improper integral converges when that improper integral leads to a finite answer. Okay, so if, on the other hand, the integral ends up being divergent as having an infinite value, or perhaps ending up with a limit that does not exist, in that case, the improper integral, would be divergent. So the integral test for convergence of series states that if the improper integral consisting of the integral from 1 to positive infinity of f of x dx converges, then the series corresponding to the sequence un is convergent. Okay, so the improper integral and the series converge together or diverge together. However, it's very important to note that the integral and the series do not necessarily converge to the same value. The integral test just tells us that the series converges, but it does not really give us the limit of that series. Okay, so let's just consider this example here. So we are given the series from 1 to positive infinity of 1 over n square root of n. So this is the general term of the corresponding sequence. So let's just call it un, which we could refer to as f of n, which is 1 over n square root of n. And I need to use the integral test in order to test the convergence of the series. So I start by considering the integral from 1 to positive infinity. Let's just call this integral I of f of n dn. You could just use f of x dx. It doesn't really matter. This is a variable. So the integral from 1 to positive infinity of 1 over n square root n, that's the equivalence of n to the 3 over 2. Okay, so here, in fact, that would be the limit when b approaches positive infinity of the integral from 1 to b of 1 over n to the 3 over 2 dn. Now, the antiderivative of this function, this is a function in the form 1 over x to the n. So applying that rule would in fact lead us to negative 1 over 3 over 2 minus 1 is half times n to the half. Our variable here is n, it's not x. So between 1 and b. So let's just fix this up a bit. So that's the limit when b is approaching positive infinity of negative 2 over square root of n between 1 and b. So let's just apply the bounds. So this is the limit when b is approaching positive infinity of negative 2 over square root of b plus 2. Okay, so over here, negative 2 over square root of b, as b approaches infinity, this approaches 0, which leaves me with a limit equals to 2. So I is convergent. We ended up with a finite value of the improper integral. So I is convergent. Then in this case, the series going from where n goes from 1 to infinity of un is in fact convergent. I remind you that this does not really give me the limit of the series, but however, the integral test actually helped me determine that that limit exists, that the series is convergent. Now, if we move to another test of convergence, which is the p-series test, which, by the way, this test could also be applied to the series that we just solved in the previous example. A p-series is in fact a series whose general term can be written in the form 1 over n to the p, where p is a real constant. Now, the p-series, in fact, help us determine the convergence of the series based on the value of p. The p-series test state that if p is greater than 1, in that case, the series is convergent. However, if p is smaller or equals to 1, then the series is divergent. And the p-series test can be easily justified using the integral test. If we go back just a bit to the previous example, you'd notice that this series is general term. I was able to write it in the form 1 over n to the 3 over 2. So this is a p-series because its general term can be written in the form 1 over n to the p, where p in this case is 3 over 2. So p is greater than 1, and this is why we ended up with a convergent series. So the p-series test can be easily justified using the integral test the same way we proved this series convergent using the integral test for convergence. So whenever you have a p-series, if p is greater than 1, you can immediately just state that the series is convergent by the p-series test, and if p is smaller or equals to 1, then the series is divergent by the p-series test. So let's just look at these two examples for the moment. Now, this series can in fact be written as the sum where n goes from 1 to infinity of 1 over n to the 1/3. Now, over here, this is a p-series where p is equal to 1/3. So p is smaller than 1, then the series is divergent. And of course, whenever you use a specific test to determine the convergence or divergence of the series, you'd have to in fact state that it's done by the p-series test. Okay? So if we observe this for the moment, if we factor out that 2, you'd notice that the series would in fact be 1 plus 1 over 4 plus 1 over 9 plus 1 over 16, etc. So this is for n equals to 1, this is for n equals to 2, this is for n equals to 3, this is for n equals to 4, etc. So we can in fact write the general term here as the series where n goes from 1 to infinity of 1 over n to n squared. That's n squared, yes. So when n is 1 is just 1, when n is 2 is 1 over 4, when n is 3 is 1 over 9, etc. Okay, so this is in fact a p-series with p equals to 2. P is greater than 1, then the series in fact is we could also write it as 2 over n squared. The series is in fact convergent by the p-series test. Okay? Now over here, if we move to the third test of convergence. Now before we tackle the comparison test, let's just discuss a small definition here. A sequence. Now this definition discusses sequences. Now if a sequence is monotonic, what does it mean it's monotonic? A monotonic sequence is in fact a sequence that is always increasing or always decreasing. So the sequence would not in fact change variations at any point for all n. So it either starts increasing and it keeps increasing, or it starts decreasing and it keeps decreasing. Now this is a monotonic sequence. Now the theorem states that if a sequence is bounded and monotonic, then we can immediately deduce that the sequence is convergent. Now this theorem helps us determine if a sequence is convergent. However, we have seen in the previous video that a sequence that is convergent does not necessarily lead to its corresponding series being convergent. The corresponding series could be both convergent or divergent. So a bounded sequence would in fact mean that you can write the terms of the sequence between two finite real numbers. This is what a bounded sequence is. It's when all its terms are bounded between these two finite numbers. And we just said that monotonic is either increasing or always decreasing. So this theorem states that if a sequence is bounded and monotonic, then it is convergent. For example, if we just discuss this intuitively, if I just know that the sequence is bounded between A and B, if the sequence is decreasing, it would in fact, this is apparently increasing. So if a sequence starts increasing and then it keeps on increasing infinitely, well, I know it cannot pass the value of b. So in that case, we know that the limit of the sequence is somewhere here. Similarly, if the sequence is decreasing infinitely, and I know it is bounded by a, it does not pass the value of a, then we know that the limit of the sequence would in fact be somewhere here, since a and b are finite. However, over here in a similar reasoning, we can determine if a sequence is convergent or even divergent using the comparison test. Now, the comparison test would in fact use two series where you'd know the convergence or the divergence of one of them, and you'd use that convergence or divergence in order to determine the convergence of the one you know nothing about. So, for example here, it's called a comparison test because I'm dealing here with two series where their corresponding sequences an and bn in fact compare this way. We'd have that, for example, an is smaller than bn for all n, and of course here an and bn must both be positive. So if we're dealing with two positive sequences where an and bn are where an is smaller than bn, in that case the comparison test states the following: if the series bn is convergent, then an is convergent, and which actually makes sense because if an is always smaller than bn, in that case, if this has a finite limit, and I know that an never surpasses bn, in that case an would definitely be, the series of course would definitely be convergent. Over here L, which is the limit of the series. Okay, and similarly over here, if you look at it the other way around, bn being always greater than an, if I know that the series corresponding to AN is divergent, so AN, its corresponding series is divergent. For example, it goes all the way to infinity, and being always smaller than Bn, then it takes this, the sum or the series corresponding to Bn along with it to infinity. Okay, so over here, if I have An smaller than Bn, where An and Bn are two positive sequences, in that case, if the sum of Bn is convergent, then An being always smaller than Bn, then the series corresponding to An would converge along. And if the series or the sum of the Ans is divergent, An being always smaller than Bn, then the sum of the Bns is divergent as well. So over here, let's just look at this series. Now, sometimes you might have to find the second series, a second convenient series that you know the convergence or the divergence to, and use the comparison test with the series that you already have. So over here, let's just call here An the sequence defined by sine squared n over 3 to the n. Now, sine squared, now in order to be able to figure out what the second series could possibly be, just observe the series that you have or the sequence that you have and try to more or less analyze on it. For example, here I know that sine n is between -1 and 1 for all n, right? So sine squared would in fact be between 0 and 1. So sine squared being always smaller than 1 and 3 to the n being always positive, then dividing here by both sides by 3 to the n, I would in fact have An. Now this is An smaller than 1 over 3 to the n, and that's for all n, for all natural numbers, and since here n is defined from 0 to positive infinity. So we just found our other sequence. We just found the sequence Bn. So we let An to be equals to this, and Bn being equal to 1 over 3 to the n. Now, the reason why I could work with Bn as 1 over 3 to the n is because this series, the corresponding series to the sequence Bn, we know the convergence to. So over here, we have that An is smaller than Bn for all natural numbers n. However, what can we say about the convergence of the series corresponding to Bn? Would that in fact be convergent, divergent, and why? So if we look at Bn, Bn is in fact a geometric series. So in fact, Bn is a geometric sequence where the corresponding series would be a geometric series. And over here, so Bn is a geometric sequence. So Bn being a geometric sequence with, usually when we identify geometric sequences or even arithmetic sequences, we'd have to point out the first term and the common ratio or difference depending on the type of the sequence. So Bn is a geometric sequence with u0. Over here we're starting with n equals to 0, with u0 equals to 1 and r equals to 1/3. So the absolute value of r is smaller than 1. Then the sum of the Bn's, where n goes from 0 to infinity, is convergent. So we have that An is smaller than Bn with the sum of the Bn's convergent. Then we deduce that the sum when n goes from 0 to infinity of the An's is convergent, and we'd have to mention that we deduce this by the comparison test. So these are the first 3 tests of convergence of series. In the following lesson, we're going to tackle the remaining tests of convergence.